Hello everyone, thanks for your attending. I'm Xianggao from National University of Singapore. I will present fast testing-based data augmentation to improve robustness of deep neural network. This work was mainly done when I was an intern at Fujitsu Lab of America. This is a joint work with Ripon Saha, Mukul Prasad, and Abhik Richardson. In recent years, neural networks are widely applied in many applications, such as autonomous driving and medical diagnosis, and so on. By training a model on the training dataset, AI model could achieve good accuracy on the testing site. However, good accuracy does not mean good robustness. That is, if we slightly perturb the testing site, the model will misclassify them. For instance, the model could correctly classify an image. However, after rotating the image a little bit, the model misclassifies it. In this project, we target to improve the robustness of AI model from the perspective of software engineering. Data augmentation is an approach to improve the performance of AI models. Similarly, it can also be used to improve the model robustness. In a widely used setting, people first find some representative perturbations of the training dataset in each epoch, and then train the model using those perturbations. However, generating representative perturbation is not easy, especially when the space of perturbation is huge. So the first challenge lies in how to identify representative perturbation from huge space. Existing approach randomly generate perturbations. As shown in our evaluation, those approaches are not effective enough. Our second challenge is that data augmentation must be efficient enough to save the valuable training time. Let's see some background of fuzzing first. Greybox fuzzing is a widely studied test case generation technique. Typically, given some seed input, you mutate the seed input to generate a set of mutations. Then you will test the program on the mutations and return the interesting ones that can improve the coverage. Based on that, you will put the interesting test as new seed, and this process continues with the goal of achieving higher code coverage. Our insight here is that the interactive nature of fuzzing gets overlaid on the multi-epoch training of DNA. To improve the robustness of AI model, we investigate a new data augmentation based on fuzzing-based approach. Here is the overall structure of fuzzing-based data augmentation. Basically, for each data point in each epoch, we train the model using its representative perturbation. This representative perturbation is also used as the seed image of the next epoch. This process is similar to the fuzzing loop. Our data augmentation is composed of two components. The first component generates representative perturbation by first generating a set of perturbation population, and then select the most interesting ones. The second component is selective augmentation. Our insight is that not all data points in the training dataset are difficult to learn. We may selectively augment part of the example in the training set that may confuse the model. Now let me give more details of two components. In the normal training formulation, the training goal is to minimize the loss over the whole training set. To generate a robust model, instead of minimize the loss over the original dataset, the new formulation assumes we first perturb the training set and minimize the loss over the worst perturbation of the training set. Here is an example with two transformations. In the first epoch, we train the model using the original image. From the second epoch, we first generate a set of perturbations and select the worst perturbation with highest loss. The selected perturbation will be used to train the model in the second epoch, and also it will be used as the seed image in the third epoch. This process continues until we train a robust model. As I just mentioned, conventional method augment each data point, which is not efficient. We save significant amount of training time by skipping some of data points presented as red cells. Our main idea is that we can skip to augment some data point that is already pointwise robust. We define the pointwise robustness based on loss. For a given data point x, we first generate its perturbations and generate the corresponding loss. If the maximized loss is less than a threshold, we regard x as a pointwise robust point, which will be skipped in the selective augmentation. We implemented our idea in a tool called Sensei and evaluate it on 5 widely used image datasets and 15 existing models. We evaluate the robustness using robust accuracy. Basically, a data point is regarded to be robust if all its realistic variations are correctly classified. Under this setting, the robust accuracy measures the percentage of robust data points. We define the space of realistic variations using 6 transformation operators, which include 3 spatial transformations and 3 non-spatial transformations. We choose the transformation parameter according to existing papers. Those transformation parameters make sure the variations are still valid image. For instance, we restrict the rotation range from -30 degrees to 30 degrees to make sure the rotated image is still valid. To evaluate the effectiveness of Sensei, we compare it with several baselines. Original model does not perform any data augmentation. Random approach randomly augments the dataset. Most often is the state-of-the-art approach proposed by Angstrom et al. We compare the robustness accuracy of those approaches. Our evaluate results show that Sensei can improve the robust accuracy on all 15 models by up to 12%. Further, we evaluate the effectiveness of selective augmentation by measuring the training time. Our evaluation results show that selective augmentation can reduce the average training time by 25% while does not lose too much robust accuracy. On conclusion, we propose a fuzzing-based data augmentation to improve the robustness of AI models. We implement a tool called Sensei, which is open source available. Compared with state-of-the-art, Sensei improved the robust accuracy by 5.5% on average and reduced the training time by 25%. So this also led to the end of my presentation. Thank you so much.